Hey everyone, and welcome to The Explainer. So every single time you stream a 4K movie, blindly scroll through your feed, or ask an AI to write an email for you, you're actually participating in one of the most fascinating, and honestly kind of existential, thermodynamic battles going on in the world right now. Today, we're diving deep into the physical layouts of data centers and their absolutely relentless fight against heat. We're going to look closely at how the physical architecture of these massive buildings literally dictates whether the apps we rely on every day survive or just completely shut down.
To really wrap your head around this, you have to think about it this way. A server is, at its core, just a massively expensive space heater that happens to do math. I mean, think about it. Every single ounce of electrical energy we pump into a CPU eventually turns into thermal energy, heat. And if you don't pull that heat away instantly, your silicon hits its thermal junction limit and just dies, shuts off. It isn't some minor software glitch. It is a hard, physical brick wall that knocks your data offline.
Now, if you're fighting a battle, you need a way to keep score, right? In data centers, that score is a metric called PUE, or Power Usage Effectiveness. This is the absolute gold standard for measuring a facility's efficiency. It literally tells us how much of a building's massive power budget actually goes toward, doing the math, versus how much is strictly dedicated to the thermodynamic nightmare of preventing those expensive space heaters from melting themselves into slag. It is honestly mind-blowing just how large a chunk of our global energy budget goes purely into cooling.
Now, back in the day, the industry relied on a legacy approach that we call chaos cooling. And yeah, it was exactly what it sounds like. Engineers would basically just blast freezing cold air from standard AC units into a giant room full of scattered servers. But here's the catch. Servers suck air in through the front and blow scorching hot exhaust out the back. So if your racks are just randomly scattered everywhere, the hot exhaust from one rack gets sucked directly into the cold intake of the rack right behind it. This creates this chaotic, messy cloud of mixed hot and cold air. It completely destroys your thermodynamic efficiency and sends that PUE metric we just talked about absolutely skyrocketing.
So to fix that mess, engineers had to get a lot more disciplined. Section 1, the alternating aisle topology. Instead of just putting servers wherever they happen to fit, you line them up front to front and back to back. But actually, just lining them up isn't quite enough. We have to take it a step further. Section 2, hot aisle containment. This is essentially the golden diagram of data center cooling. Let's actually trace the exact fluid dynamics of how this containment system works, because it's brilliant. By physically walling off the hot exhaust, we let the rest of the massive data center room act as a giant, safe reservoir of cold air. Step 1, cold air is pumped into the open room, usually up through a raised floor. Step 2, the server fans actively pull that cold air right through the front panel in the cold aisle. Step 3, the air squeezes tightly over the CPU heat sinks, absorbing all that intense thermal energy. Step 4, that air, which is now incredibly hot, gets aggressively pushed out the back into the hot aisle. Step 5, and here's the magic, that hot air is physically trapped. We're talking doors on the ends of the aisle and a solid roof on top. And finally, step 6, since it's trapped, it has nowhere to go but straight up, where it's sucked into the ceiling return plenum and routed right back to the chilling units. Pumped, pulled, pushed, trapped, and sucked. Zero mixing. Maximum thermodynamic efficiency. It's an incredibly elegant system, but, well, this brilliant engineering is currently hitting a massive physical wall. Section 3, the AI escalation, and how it's breaking air cooling.
To really grasp the scale of the problem we're facing today, we have to look at one massive number, 100 plus kilowatts. Traditionally, a standard server rack pulled maybe 5 kilowatts of power. Today, with the absolute boom in deep learning and these gigantic GPUs, extreme AI racks are jumping from 5 to 40 to 50 and even over 100 kilowatts per single rack. The stark, unavoidable reality of physics here is that air simply lacks the specific heat capacity to remove that volume of thermal energy fast enough. You can only move so much air before the servers literally just cook themselves.
So, what's the solution? Next-gen liquid cooling. And it all comes down to this staggering superpower. 3000x. Liquid is up to 3,000 times more effective at transferring heat than air. When we're talking about next-generation AI workloads, liquid cooling isn't just some nice-to-have luxury. It is a literal fundamental requirement just to keep the silicon alive.
Now, there are two really fascinating ways the industry is rolling out this liquid superpower. First, we have direct-to-chip or cold plate cooling. Instead of slapping a bulky metal heatsink and a loud spinning fan onto a chip, a closed-loop microchannel plate is bolted directly onto the CPU or GPU. Coolant fluid flows right through the plate, absorbing the heat with closed-loop precision directly at the silicon level. Then we have the extreme solution, immersion cooling. Imagine taking an entire server rack, the whole shebang, and just dunking it into a tank of engineered non-conductive dielectric fluid. The fluid boils at a really low temperature, turns into a vapor, hits a condenser at the top of the tank, and literally rains back down onto the servers. It's a completely wild concept, right? Boiling liquid that somehow doesn't short-circuit the electronics, but it gives you a completely fanless, near-silent, hyper-efficient system.
When we put legacy HVAC head-to-head with next-gen liquid cooling, the trade-offs are pretty undeniable. Liquid absolutely dominates in heat transfer and silent operation, and it allows for incredibly dense AI racks shoved into very small physical spaces. Legacy air, on the other hand, requires massive, sprawling rooms, complex raised floors, incredibly high ceilings, and creates absolutely deafening noise from thousands of spinning fans. So what's the catch? Capital expenditure. Liquid demands massive initial plumbing and super specialized fluid costs up front, whereas legacy air is definitely cheaper to set up on day one. But to support the future of AI, it's a trade-off that data centers are being forced to make.
The big takeaway here is that mastering the physical layout of these facilities isn't just some abstract engineering puzzle. It is literally the only way to unlock hardware efficiency for the future. The speed of the apps you use, the reliability of cloud services, and the entire environmental footprint of artificial intelligence all depend on this evolution. We've gone all the way from fixing the absolute mess of chaos cooling with strictly disciplined hot aisle containment to understanding exactly why extreme AI workloads are forcing this massive industry shift toward liquid cooling.
But cooling is really only the physical side of hardware efficiency, which leaves us with a truly provocative question to think about. What if the CPU itself could just magically draw less power when it isn't completely busy? Take a look at this foundational equation. Power equals capacitance times voltage squared times frequency. P equals CV squared F. Modern processors can actually use this exact math to shape their own voltage in real time, saving massive amounts of energy without needing a single drop of extra cooling. It's a brilliant leap in design, and honestly, I highly encourage you to keep questioning exactly how these incredibly complex systems work under the hood.